All right, so here we are at the end of November, last week of classes, and you've got one final homework assignment that's due on Wednesday. It should be submitted to Blackboard before class. That assignment just has two problems. It's got, if I remember correctly, one that is a trickling filter and one that is a secondary settling problem. So we've had some examples that address both of those questions. Now the final exam is at the end of exam week. We've got to wait all the way till Friday to have our big party.
Best for last.
That's right, best for last. It's comprehensive, meaning that there will be material from the beginning part of the semester. And what I typically try and do is, I try and ask questions I haven't already asked on a midterm exam. So, if you learned how to do 10 different things during the first part of the course, but there was only 3 problem-solving questions, I'll probably try to pick, usually, one of the things that you haven't already been examined on. That's generally, but I'll probably forget all that when I'm actually making the test, but we'll see. It'll be the full 2-hour time period that we have. My intention is to write an exam that's about twice as long as the tests that you have in class usually. And so, ordinarily, those tests, I think the average student is out of here in 40 or 45 minutes. And so you'll have, maybe a 90-minute exam and 120 minutes to take it. You can bring all of your previous formula sheets that you've made for the earlier 2 exams and then one more as well. So, if you want to make fresh ones, it doesn't have to be those original formula sheets. Just the point is, if you already made one for the first half of the course and the second half of the course, then just to save some time, you can reuse those and then add one more on top of it. You can put anything you want on those formula sheets. I debated whether or not I should allow you to. Sometimes what I do is I split off the concept question, and so you can't use the formula sheet during the concept questions, but I decided that I don't mind if you use the formula sheet on all of it. So the exam will be all together. It won't be 2 separate sections, the concept questions and problem solving. It'll just be one continuous exam, and so if you want to put concept-related stuff on those formula sheets, then that's fine. You can do that. Any questions about the announcements? All right. So today we're going to continue talking about wastewater plant residual management. Honestly, I don't think that we'll have time to get into direct and indirect potable reuse. We may get to that on Wednesday or Friday, but I suspect that the bulk of our time on Wednesday and Friday will be related to some software stuff. So how many people here have a laptop that they could bring to class on Wednesday and Friday? Good. I see lots of hands up. For those of you who don't, you can just maybe scoot next to somebody who does have a laptop and work with them. There's going to be some software that I'll send you a link for that I'd like you to install. It's called BioWin. And it's a program that simulates wastewater treatment plants. And so you can kind of build a reactor configuration. And I think maybe Dr. Yoon had, if you remember back to 351, did some of you do wastewater simulation in his class? No? Okay. Well, he uses a different software package that's, as he describes it, maybe a little bit more buggy. So I'm hopeful that we'll have a good experience with this BioWin. I've only just started using it in the last couple of days, but there are a couple of graduate students who've been using it for longer than that, and they've developed some lessons and examples that they want to share with you. Well, I don't know if they want to, but I've assigned them to share it with you, and so that's what we'll be doing for Wednesday and Friday. So keep your eye on your email because you're going to need to install some software before you come to class on Wednesday.
Will we use that on the phone?
No. It's just for your own edification. You won't be tested on it.
Do you know if it can be used on Mac?
It can if your Mac is simulating Windows. You don't have a Windows emulator?
I do, but that is highly annoying.
I think that Macs in general are highly annoying.
Nah, they're way better.
They're way better, except for a lot of engineering software isn't written for Macs is the only problem.
They're getting there. Autodesk is getting there.
I don't know if BioWin will get there. It's a pretty small company located in Canada.
They probably will.
I don't know if they've got Apple up in Canada. All right. So here's what we're going to be talking about today. Just to refresh your memory, since it's been, I think, 9 days since our last class, what we were talking about is how the residuals are dealt with in a wastewater treatment plant. Remember, we talked about there's lots of different things besides the water that's getting discharged that need to be disposed of. There's the grit, there are other solids like that they pull out of the bar rack, there's sludge, sludge gets a lot of attention because it is bioactive. It has microorganisms that can be pathogenic. It has organic material that may continue to exert a biological oxygen demand. And so what we're going to be talking about mostly today is the considerations of how we break down and reduce the volume of the sludge and how we stabilize the sludge. And one of the common ways to deal with sludge solids is through anaerobic treatment. And just to do some compare and contrast, in an aerobic environment, this biological material that exerts a demand for oxygen, BOD or COD, about half of the carbonaceous material ends up as sludge and half of it is consumed by the aerobic bacteria along with oxygen, and they generate heat in the process of doing that. So that's their cellular respiration is consuming the BOD, and some of it ends up as sludge residuals. But in the case of anaerobic treatment, what's happening is that the organic material is largely being transformed from simple sugars and even complex carbohydrates into methane. And there's still some sludge material that results from that, but there are a variety of benefits, both reduction of volume and also the advantages of having energy-rich flammable gas that comes from that. And so we're going to watch a brief video that illustrates a little bit about this anaerobic treatment. Try and get past the commercial here. All right. All right, so if that hasn't sold you on the benefits of anaerobic digestion, I don't know what will. Essentially what we're doing is producing energy by causing a different species of microorganisms to break down the waste than could occur in an aerobic environment. And that can be applied to a lot of the different wastewater treatment steps that are upstream that are generating sludge from suspended growth, from attached growth systems, sewage lagoons. You know, all of these processes generate a sludge that could be suitable for anaerobic treatment. If we go into the kind of the chemistry of what's happening, there's two, broadly speaking, steps. An acid fermentation step, which is relatively fast, where microorganisms are breaking down complex wastes like fats and proteins that are left in the sludge and hydrolyzing them into fatty acids, amino acids, and so on. The methane fermentation is a little bit slower, and that takes the output of the acid fermentation step and is what turns it into methane and carbon dioxide. And so this is a figure that illustrates from the book the intermediate steps of propionic acid, acetic acid, but basically what the ultimate aim is for the waste that's coming in, which may be a blend of carbohydrates, fats, and proteins, that what's generated is methane gas, CO2, and then there is also, those aren't the only two end products, there's also some final residual that can't be broken down all the way, so there's always going to be some solid particles that have to be disposed of either by land application or other disposal. So the simplest approach for anaerobic digestion is just a single standard rate digester where the sludge is going into a digester and it's staying there for between 1 and 2 months. And simultaneously, the acid fermentation step and the methane fermentation is happening in the same digester at the same time. You'll see that this is stratified, meaning that inside the reactor, due to density differences, there's going to be different layers of materials, and at the top of that is the gas that has to be collected. And one of the tricks of anaerobic digesters is that the gas layer has a variable thickness depending on the temperature of the reactor, the temperature of the incoming waste, that the rate of gas production can change and the amount of gas inside of the digester can change. And so we'll look at some pictures of these digesters in the real world, and from just an operational standpoint, one of the tricky things that they have to put a lot of thought and effort into is making a gas-tight layer that can adjust in its depth. And so putting some sort of a flexible lid on these anaerobic digesters so that the gas layer can go up and down. And remember that this is a flammable gas. And so there's a whole nother set of considerations that come from that from a safety standpoint, that when you've got a flammable gas and you're pumping things in and out, you have to be pretty careful about electrical leads and lights in the buildings that house these digesters. And so we'll look at some photos that illustrates all of that. But the main thing to keep in mind is that in this standard rate digester, only about 1/3 of the volume is actively breaking down waste at any time. And the rest of it is storage for the stabilized solids, storage for the scum layer, which is these fats and oils that are either too dense or too concentrated to actually be broken down by the microorganisms inside the digester. And so this isn't very efficient. It takes a lot of time, and they've come up with different configurations to try and reduce the 30 to 60 day retention time, because if you've got a long retention time, that means that the volume of this needs to be very, very large. So whatever your rate of sludge generation is per day, if you multiply that by 30 or 60, it's going to mean a very large digester. And so to try and speed things along, a high rate anaerobic digester has been conceived where the first stage is completely mixed. And by completely mixing, what they're doing is they're dispersing the food that these anaerobic microorganisms are consuming throughout the entire volume of the reactor. And so now, instead of only 1/3 of the reactor volume being active, by having a completely mixed first layer, you're able to have that increased speed of the reaction. But it is still necessary to have a second stage where, because what we're trying to do is concentrate sludge, and so there is going to be some more dense material that needs to be collected at the bottom of the reactor, the cellular material of the microorganisms that are consuming BOD and generating gas. They'll eventually die, and they need to be collected and disposed of. And so the digested sludge is primarily the cellular material of the microorganisms that are breaking down this secondary sludge. But there is also the issues of gas storage and collection, and so all of the same complications exist with a high rate anaerobic digester. It's just, if you look at the loading rates, in the case of the standard rate digester, we'd load this with between 0.5 and 1.6 kilogram of volatile solids per cubic meter of storage volume. But in the case of a high rate digester, we can boost that up to as high as 8 kilograms per cubic meter. And so, you're quadrupling essentially the loading rate, the upper end of the loading rate that can be accommodated. And this range of loading rates is largely dependent on temperature. We'll look at the effect of temperature on a slide here in a moment, but it in part has to do with the mixing behavior inside the first stage. But what it's really dependent on is the kinetics of the microorganisms are dependent on the temperature of the environment that they're in. And so you'll see here is depicted a sludge heater. And the sludge heater can burn gas that's being generated by the reactor. So here's that slide that illustrates the effective temperature. And one of the ways that they perform calculations and estimations on how big the digester needs to be is the amount of time required to have a certain reduction in volatile suspended solids. And so if you look at the y-axis of this figure, it's the percent reduction of volatile solids. And so the sludge that's coming in, if you say want to reduce the volatile solids by 40 or 50%, then this regression analysis, the curve here is a best fit line that fits all of the data that was observed and kind of is a rule of thumb estimate. And now on the horizontal axis is temperature times time. And so in Celsius multiplied by the number of days of residence inside the reactor. And so what this is showing is that if you have cold temperatures, you could accumulate the number of degree days you need by just having a much longer storage time. But if you have relatively warm temperatures, then you can accumulate these degree days a lot more quickly. And so it pays to have a sludge heater in anaerobic digestion because you'll get the reduction in volatile solids that you need at a much faster rate than if it was just happening at the ambient temperature of the sludge that's coming in. The other thing to note about this figure is, boy, the R squared is not very good, right? If you look, there's just some outlier data, some system that observed more than a 50% reduction in volatile solids after 200 degree days, and then a similar amount of reduction took 1800 degree days. And so you really do have to have the sludge that you're going to be working with, and you do tests in the lab that have to be specific for the wastewater treatment plant that you're going to be working with. You couldn't take a design from a different treatment plant with completely different waste characteristics and extrapolate the performance of one treatment plant to another. It's really site-specific, but the general trend is undeniable that the longer the time and the warmer the temperature, the more efficient the reduction is of the suspended solids. So keeping this stuff warm is important. There's a table in our book that illustrates some of the heat transfer coefficients that exist in different environments. How many people here have taken thermodynamics? 3. I saw 3 hands. I never took thermodynamics, and so I don't know a lot about it, but let's stumble through this together. I think I understand it well enough that we can make some sense out of this. So if you have just a concrete tank that isn't insulated, then what this is showing is that the heat transfer coefficient is between 4.7 to 5.1 watts per square meter, and then you'll notice that the units here have Kelvin in the denominator. That's because when you apply this heat transfer coefficient U into the equation for heat transfer rate, there has to be a difference in temperature between the things that you're trying to insulate and where the heat is flowing to. So let's say that we've got a lot of warm sludge that we're trying to keep warm. You'd have to put insulation around the tank that's holding the sludge so that the heat doesn't go into the outside ambient air. So this little example that I've put together here of a heat transfer through an anaerobic sludge digester, we're looking at what if we had the digester operating at 112 Fahrenheit and outside air temperature is 10 degrees Fahrenheit. And we've got a cylindrical sludge digester just for ease of calculation. I mean, the reality is that these sludge digesters are very often egg-shaped, simply because that gives you volume where you need it. Remember that the layers are getting stratified, And so you need a lot of volume in that middle layer where the reaction is happening, and you don't need quite as much volume for storage up at the top. So they make a lot of these sludge digesters egg-shaped. But for ease of calculation, let's say it's cylindrical, and some of them are cylindrical. That'll just make it easier for us to calculate the outside area of this. So let's just assume that it stays all the time 112 degrees Fahrenheit for our sludge and 10 degrees Fahrenheit outside. Maybe this is in, I don't know, Norway or something. Always cold. Let's just say if we went from uninsulated to insulated, then how much power could be saved on an annual basis by doing that? So we're going to assume to begin with just a mid-range value for this concrete walls that are above ground. So you can see that a mid-range value for the heat transfer coefficient, if it's concrete walls that are above ground, if we went in the middle of that range, it would be 4.9 watts per meter squared Kelvin. But then if we insulated those concrete walls, we may get the heat transfer coefficient down as low as 0.7 watts per meter squared Kelvin. So what we're going to do is we're going to just look at what's the net savings in power that you have to apply to heat this. So the temperatures in question, T2 is the temperature of the air. And so the air temperature of 10 Fahrenheit, that corresponds to 260.93 Kelvin. Whereas the temperature of the liquid we're trying to insulate, and we assume that the tank that's holding the liquid has the same temperature as the liquid itself. So the concrete is at the temperature of the digester, which is 112 degrees Fahrenheit. So that's 317.59 Kelvin. Okay, now this is a cylindrical shape, and what we need to know is this area, the outside area of the cylinder. And let's assume that there isn't heat transfer on that top or on the bottom. We just want to know the heat transfer that's occurring on the outside vertical surface of this cylinder. So what's the formula for the outside area of a cylinder? Area is pi dh. That's right. So pi d gives us circumference, and then h turns that circumference into the area. So if you cut the top and the bottom off of a Pepsi can, for example, and you rolled it out flat, then you could get the area of that by what was the circumference, which is the top length, and then the height of it, which is the other dimension. Okay, so let me just pause for a second. I'm going to bring up my scan solution of this, but I'd like you to calculate what is the Q dot before, and then what is the Q dot after. How much heat is flowing out of this if it's uninsulated versus if it is insulated? Okay, so let's look at this. We got to calculate the area that the heat is transferring through. I think that's 212 square meters. And so we've got before it was insulated and was just plain concrete, and the heat was just really flowing through there a lot. And then after insulation, the heat is flowing through much more slowly. So before, it is 58.8 kilowatts flowing out, which that's an enormous amount of heat flowing out, because I've intentionally selected a pretty extreme example, you know, like just the bare concrete and really extreme temperature differential. If the temperature differential was less, then the heat flow would be less. And of course, we see once it's insulated, we can get by with a lot less heat, having to, not having to add quite as much. So over the course of a year, we could save 400,000 kilowatt hours if this was being electrically heated. Now, for obvious reasons, you don't do that. There's more efficient ways than just a resistive heater to warm things up. You could use a heat pump, and then you're using maybe a fifth of the electricity compared to electric resistive heating. Or you could just burn the methane that's being generated, and that's usually sufficient to keep things toasty and warm if it's well insulated. I don't think it would be enough energy to keep it toasty and warm the rate that the methane is being generated if it was non-insulated. So, any questions about that illustration? Okay. So the tricky thing is that we want to mix the first stage, but we've got an explosive gas. And so, we may not want to have like a pump on the roof, a pump connected to a motor that's spinning things around. And the fact that the roof is going up and down because the volume of gas that's being stored can change over time, it introduces some challenges. And so what a lot of places seem to have done to keep it mixed without having to have mechanical parts in or around the digester is they're using a gas compressor and a diffuser at the bottom. So they're collecting some of the gas off the top and then sending that through a compressor and diffusing it inside of the digester, and then that keeps it mixed, because as the gas bubbles rise, it causes a current to set up. So that's one way to do it. Now, the fact that the gas volume may be rising and falling means that sometimes what they'll do is they'll have like a membrane at the top that can be floating on top of the sludge, and then they'll have to have different kinds of like buoyant, I don't know what to call it, some sort of a flotation system that can support the weight of all of the materials that are built into the roof. And then also it has to be a gas-tight seal, because this valuable gas you don't want to be leaking, and also the gas can have hydrogen sulfide in it, which is corrosive, and all of it's flammable to begin with. So here are a couple of pictures of anaerobic digesters, and ironically, if you look at this one, it's just bare concrete. And I don't know if it's maybe insulated on the inside rather than the outside. That may be the case, that it's concrete on the outside, but then hopefully it's insulated somehow, because we just went through the calculations and showed what a waste that is to have it uninsulated concrete. But this shows you the challenges that they face of having a cover that's going to be rising and falling. Let me dim the lights, and so this is a little bit easier for you to see. They've got a rigid pipe up to the edge of the wall, and so this elevation may be going up or down, and so they've got a flexible section of all of these pipes that the gas can still be flowing through here. It's compressed gas lines, just like we showed on the previous slide, where they're taking the gas and introducing it at the bottom of the digester to mix the sludge. And so this has to be flexible, because sometimes this is going to be relatively empty, sometimes it's going to be relatively full. It looks like it's pretty near the top. You can see that there are some wheels on the sides that help to keep the cover aligned and centered, so it's not going to bump up against it, but then it's got kind of like a rubber floating ring around the top that allows this entire roof to float on top of the sludge. Lightning arresters, if we wondered from this earlier slide what all of these wires sticking up are, I guess that would be bad if the whole thing got struck by lightning, because we've got a flammable gas that's been collected. So those are lightning arresters, and there's also a sensor that's sending data out to the operator of the roof level. So it's just measuring the distance between the roof and some arm that's hanging over it, and it's probably like a ultrasonic sensor that's just reporting back the distance between the two objects. There's a building next to this digester where all of the pumps are housed, and because it's pumping an explosive gas, a flammable gas, they have to have light switches and lights that won't produce any kind of an arc that could cause a fire. So that ups the cost quite a lot to have these explosion-proof light fixtures. Besides those challenges of operation and so on, other challenges of anaerobic treatment are that anaerobic treatment's really slow, and so the reactors have to be pretty large, and it may, because of the formation of a lot of acid, it may require the addition of alkalinity, because if all of the alkalinity is consumed that's in the water, then the pH could get so low that the chemical process is stalled or slowed down. So sometimes it requires the addition of alkalinity to prevent that from happening. Compared to aerobic treatment, the sludge that comes out of it, or not the sludge, but the supernatant. Let me show you the layer. So this supernatant layer is the water that's coming out that we could conceivably discharge to a river if it had low enough BOD, but the supernatant in anaerobic treatment has a high enough BOD that it's just returned to the very first step in the treatment process, and it goes through all of the primary and secondary treatment another time to try and remove BOD. So aerobic treatment has a supernatant with improved quality compared to anaerobic treatment. The suspended solids are higher than they would be in aerobic treatment, and because it's so slow, then there's a long startup time where if you have some sort of a shock or like a toxic come through the system and wipe out all of the microbes that are living in a sludge digester, it can take months to reach equilibrium again. And so it's just a long time that your process isn't working, and you're having to dispose of the sludge until you've got a good population of bacteria in there, and it's removing the BOD and generating the gas. And so that long startup time can have a lot of headaches associated with it, and expense as well. Nutrient removal isn't possible in traditional systems. There have to be other steps along the way to have the removal of nutrients. It can't be done just in kind of a single stage, and it's very sensitive to temperature changes, and if toxic materials come through, the microorganisms that live in an anaerobic environment are very sensitive to those, and like it said in the earlier bullet point, the startup time, if you do have a kill of all the microorganisms, is very lengthy. Finally, the gas is not only is it flammable, but hydrogen sulfide, when it forms, is corrosive, and so you're recirculating this gas to mix the anaerobic waste in that digester, but it can break down the pipes and the pumps if it has hydrogen sulfide in it, and also the odor is bad, but hopefully the odor isn't an issue. The odor is only an issue if gas is leaking around the seals of the digester, but the corrosive gas accumulation can be a problem even if things are well sealed. So that's all the time we have for today. Let's just revisit these announcements one more time. All right, so Remember to keep your eye on the email because I'm going to give you some instructions on installing the BioWin software. And then bring that to class on Wednesday because Wednesday and Friday we're largely going to be working through BioWin simulations. So I'll see you in class on Wednesday.